So Maclaurian series is defined by this expression. Yeah. So any function f, we can show that through application of derivatives. Any function of x can be expanded about x equal to 0 like this. F of 0 into x by 1 factorial into f dash 0 plus x square by 2 factorial into f double dash 0 plus x cube by 3 factorial times f triple dash 0 and so on till infinity. Now when we do this Taylor series expansion about x equal to 0, that is Maclaurin series. So this is the Maclaurin series. When we do this, we get these expressions. E power x is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial and so on. These we have to remember. Okay. E power x. Then a power x is same like e power x, but wherever x comes, you have to multiply with logarithm of a. So a power x is equal to 1 plus x log a by 1 factorial plus x square into log a the whole square by 2 factorial plus x cube by log a the whole cube by 3 factorial, so on. Now 1 plus x whole power n, you don't have to worry. This is binomial expansion. I'm telling the important series that you need to remember. Then the fourth one, log of 1 plus x is x minus x square by 2 plus x cube by 3 plus x power 4 by 4, so on. All right. These three, or at least the first two, and the last one, at least the two terms, first two terms are very important. So sin x is x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial. There's a pattern. You see that. Alternative positive and alternative negative signs, and the powers go as 1, 3, 5, 7, and denominators go 1 factorial, 3 factorial, 5 factorial, 7 factorial. With cos, it begins with 1 and it goes into even powers by even factorials. So this is what you get. Now there is a valid proof for it. This is something very useful. You see, I have given this Maclaurin series expansions up to a certain limit, certain number of terms. So carefully observe here, sin x, x minus x cube by 3 factorial plus x power 5 by 5 factorial plus x power 7 by 7 factorial, so on. All right. Now observe here, if I use only one term of just one term of the Maclaurin series. What is the first term of Maclaurin series of sin x? X. So y equal to x I use. Now y equal to x and sin x, they tend to match only when x is close to 0. When x tends to 0, sin x will be equal to x. All right. Otherwise, it is not matching. However, look at I add one more term of the Maclaurin series. You see here, I suppress y equal to x. When I add one more term of the Maclaurin series, y equal to x cube by 3 factorial. You see a bigger portion of the graph is overlapping. I add now 1, 2, 3, 4, 4 more terms of the Maclaurin series. You see how much portion of the graph is coinciding, and finally I add more terms. This is 1, 2, 3, 4, 5, 6, 7, 8, 9 terms almost, or 8 terms, and you see how much it is overlapping. So as Maclaurin series tends to infinity, the whole curve will overlap. That's the idea. But when we are around x equal to 0, the first 2 or 3 terms are sufficient. Okay, that was series expansion of a sine function. We'll look at for cos also, it will be the same. I will do it quickly. For cos, now cos x graph, cos x Maclaurin series is this. Here, 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial. So when I put 1, there is hardly any match. Only at x equal to 0, it is a match. When I put 2 curves, 2 terms of the Maclaurin series, so there is overlap in certain portion of the curve. When I put 3 terms, you see a greater portion of the curve is having an overlap. Then I add 3 more terms. A greater portion has an overlap. 2 more terms. Greater portion has the overlap, you can see. So as the number of terms of the Maclaurin series increases, the curves overlap. So that we saw for cos also. And now we will see for e power x graph. So this is the e power x graph, which goes to positive infinity as x tends to infinity, and it tends to 0 as x tends to minus infinity. Okay, this is the graph of the exponential function. When you put y equal to 1, the first term of Maclaurin series, it is not at all matching. Second term, it is just tangent at 0 at x equal to 0. All right, next term I add. Now it is getting closer. Same tangent at that point. Now I'm suppressing y equal to 1. I'm suppressing y equal to 1 plus x. There's an overlap. There's a small portion of the curve that overlaps. Then I add 1 more term. Then I add 7 terms. You see the overlap. And then 2 more terms. You see the overlap. So right hand side you can see is totally getting overlapped. So of course, as the x tends to the number of terms tends to infinity, there will be an overlap. Okay, so this is Maclaurin series expansions, which are very, very useful. These are all true, but you should know the scope where they are true. They're not true away from the origin. They are true close to the origin. But as number of terms go to infinity, then the curves match. So that was a very useful series expansion. Now, based on this, now we need to do our other results. Trigonometric we finished. We will do logarithmic and the first portion of the exponential. These two we can easily complete. So these two are easy to solve using the Maclaurin series expansion. So log of 1 plus x, we see, I will solve it here itself. I'm solving here limit x tends to 0, I will replace with the Maclaurin series. Log of 1 plus x is, you see at the top here, x minus x square by 2 plus x cube by 3 minus x power 4 by 4 plus so on, divided by x, which is equal to limit x tends to 0, 1 minus x by 2 plus x square by 3 minus x cube by 4, so on. Now, as x tends to 0, it will be 1 minus 0 plus 0 minus 0, so on. The value is 1. So remember this limit. This is the standard limit. Log of 1 plus x upon x is equal to 1. Similarly, limit e power x minus 1 upon x is equal to 1, and limit a power x minus 1 by x is equal to log a to the base e, because we will convert a power x, we can use a conversion to e. All right, we can convert that to e. So this is e power log a to the base e whole power x. A is nothing but e power log a to the base e. All right. So we get e power x into log a to the base e. So that's why when e power x minus 1 by x equal to 1, a power x minus 1 by x will be equal to the coefficient of x, log a to the base e. So these are the important results. Now, based